Right now, at this very moment, you are falling through a hole in space. Not a black hole, not a wormhole, something far more unsettling, a cosmic void stretching 2 billion light-years across. Scientists confirmed this back in 2013, yet most people still have no idea we're living inside it. This isn't science fiction. This is our reality. We exist inside what astronomers call the KBC void, a cosmic desert where matter itself is 20% thinner than it should be. Think about that. 1/5 of the material that should surround us simply isn't there. And this emptiness? It's doing something extraordinary. It's warping our measurements of reality itself. The universe appears to expand faster here than anywhere else, breaking our most fundamental equations. The laws we thought governed everything might only be local rules, distorted by the hole we're trapped inside. Here's what we're about to explore together. We'll journey through the discovery that shattered modern cosmology. We'll understand why 90% of space is hollow, and we'll reveal what it truly means to exist on the cosmic outskirts in a place we were never supposed to be. If you're ready to see the universe differently, to understand that everything you thought you knew might be viewed through a cosmic lens we never accounted for, then stay with me. Because what comes next changes everything. 3 astronomers were doing routine work when reality broke. Ryan Keenan, Amy Barger, and Lennox Cowie were counting galaxies in 2013, mapping their positions across billions of light-years of space. Standard cosmological survey work, nothing unusual. Until the numbers stopped making sense. Everywhere they looked near Earth, galaxies were missing. Not slightly fewer, 20% fewer. The pattern stretched outward in every direction for 1 billion light-years, forming a perfect sphere of cosmic emptiness. And we were sitting near the center. This wasn't a small gap between galaxy clusters. This was a void on a scale that shouldn't exist according to everything we understand about how the universe works. They checked their data, triple-checked it, used multiple galaxy surveys, examined the sky from different angles. The result never changed. Our galaxy, everything around it for 1 billion light-years, sits inside an underdense bubble of space so massive it dwarfs every other structure we've ever observed. The discovery earned a casual-sounding name, the KBC void, using the initials of its 3 discoverers. But there's nothing casual about what it represents. According to the standard model of cosmology, the universe should be roughly uniform when you zoom out far enough. Sure, galaxies cluster together and leave empty spaces between them, that's expected. But a region this enormous, with such a significant deficit of matter, that pushes beyond what random chance can explain. Computer simulations of cosmic evolution from the Big Bang rarely produce voids this large and empty. When they do, it requires exceptionally rare initial conditions. The statistical probability clocks in at less than 1 in 1,000. Some scientists calculated it would take a 10 sigma deviation from average density. That's so unlikely you might not find one in the entire observable universe. Yet here we are, living inside one. The implications began cascading immediately, like dominoes falling in slow motion across the field of cosmology. If we live in such an unusual location, does that bias every measurement we make? When we point our telescopes at distant supernovae to measure cosmic expansion, are we seeing the true rate or a distorted local version? The void hypothesis offered an answer to one of the biggest mysteries in modern cosmology, the Hubble tension. For years, scientists have measured 2 different expansion rates, depending on whether they examine the ancient universe or the nearby universe. The numbers disagree by 9%. That sounds small, but it represents a genuine crisis. Both measurements are incredibly precise. Both should give the same answer. They don't. Here's where the void changes everything. If Earth sits inside a massive, underdense region, gravity from the denser matter surrounding the void pulls outward on galaxies within it. That extra pull adds velocity to their motion away from us, making local expansion appear faster than average. Suddenly, the conflicting measurements make sense. We're not measuring the universe incorrectly, we're measuring it from inside a hole. This realization changed everything in cosmology. But it also raised an uncomfortable question that scientists are still grappling with. A question that strikes at the heart of how we understand reality itself. If our location is this unusual, can we trust anything we think we know about the cosmos? The answer is far more disturbing than anyone expected. And what comes next reveals just how strange our cosmic neighborhood really is, stranger than we ever imagined possible. The nature of cosmic voids. Cosmic voids are not truly empty, which makes them even stranger than their name suggests. Between the lonely galaxies scattered through these regions stretches space that contains mainly dark matter, dark energy, and occasional wisps of hydrogen gas. The density is so low that gravity barely functions. Without enough mass to pull things together, structure formation essentially stops. No new galaxy clusters can form. No rich superclusters emerge. The void stays a void, frozen in a state of perpetual emptiness. This emptiness has consequences that ripple through physics itself. Gravity is already the weakest fundamental force in nature, requiring enormous masses like planets and stars to show noticeable effects. In a void where mass is scarce, gravity becomes even less relevant. The dominant force becomes dark energy, the mysterious pressure that accelerates cosmic expansion. In dense regions full of galaxies, gravity fights against dark energy, slowing down expansion in those areas. Inside voids, gravity loses that tug of war. Dark energy wins decisively. As a result, voids expand faster than the rest of the universe. They grow like bubbles, pushing their boundaries outward while the filaments of galaxies around them act as walls. This creates a self-reinforcing cycle. The more a void expands, the emptier it becomes, which allows even faster expansion. Scientists confirmed this through careful observation. They measured how galaxies near void edges move compared to galaxies in denser regions. The void galaxies are rushing away from the center faster than cosmic expansion alone would explain. Something is pushing them outward. That something is the gravitational pull from all the matter outside the void. Think of a void as a valley surrounded by mountains. Gravity pulls downhill from the mountains toward the valley. But since we're talking about space rather than terrain, that pull makes galaxies fall outward, not inward. The effect is measurable and significant. Our own galaxy is moving away from the local void at 600,000 miles per hour, driven by this gravitational imbalance. The interior of a void becomes a strange place for physics. Light travels through it, experiencing less gravitational influence than light passing through normal space. This affects observations in subtle ways. When astronomers study the cosmic microwave background radiation, the faint afterglow of the Big Bang, they notice that light passing through voids appears slightly cooler. The reduced gravity in voids causes less gravitational redshift, showing up as cold spots in temperature maps of the early universe. These cold spots line up perfectly with where we observe large voids today. This alignment is not coincidence, it's physics in action. Understanding what makes voids empty helps explain why they matter so much to cosmology. They're not just boring blank spaces between interesting galaxy clusters. They're laboratories where dark energy dominates and where gravity takes a back seat. By studying how matter behaves differently in voids versus dense regions, scientists can test fundamental theories about how the universe works. The KBC void around us might be unsettling because it makes us question our cosmic typicality, but it also offers a rare opportunity. We're positioned in exactly the right place to study the universe's most extreme, low-density environments up close. The structure that contains these voids is far stranger than anyone imagined. The universe is not a smooth soup of evenly distributed galaxies. Instead, it resembles Swiss cheese, where dense matter forms walls and filaments surrounding enormous hollow pockets. This foam-like architecture is called the cosmic web, and it represents the largest structure in nature. Galaxy clusters concentrate at the intersections where multiple filaments meet, creating nodes of intense matter density. These nodes shine brilliantly, with millions of galaxies packed relatively close together. Stretching between them run filaments, long chains of galaxy groups that can extend for hundreds of millions of light years. These filaments form walls, vast sheets where galaxies gather in higher than average concentrations. Between the filaments and walls lie the voids, taking up most of the volume while containing hardly any mass. This structure wasn't always obvious. For decades, astronomers photographed the sky and counted galaxies. But the true three-dimensional arrangement remained hidden. Distance measurements were poor. Galaxies that appeared next to each other might actually be separated by billions of light years, with one much farther away than the other. Only when scientists began measuring galaxy redshifts systematically in the 1,970 seconds and 80 seconds did the cosmic web reveal itself. Redshift surveys allowed astronomers to calculate how far away each galaxy was by measuring how much the expansion of space had stretched its light toward redder wavelengths. Suddenly, the distribution snapped into focus. The universe had structure on scales nobody expected. The first major void discovery came in 1978, when two independent teams identified large underdense regions. More surveys followed, each mapping deeper into space and revealing an increasingly intricate web. The Sloan Digital Sky Survey, which began in 2000, created spectacular three-dimensional maps spanning billions of light years. These maps show the cosmic web in stunning detail. Filaments twist and branch like blood vessels. Voids appear as dark bubbles, sometimes 500 million light-years across. The largest structures include the Sloan Great Wall, a filament nearly 1.5 billion light-years long. On the opposite end of the spectrum, supervoids like the Eridanus void stretch 1.8 billion light-years wide, with even fewer galaxies than the KBC void. Together, these features paint a picture of a universe organized on scales far larger than anyone predicted. Galaxies are not the fundamental building blocks. The web itself is the structure, with galaxies just marking where matter happens to concentrate. Why does the universe organize this way? The answer reaches back to the beginning. Immediately after the Big Bang, matter was not perfectly uniform. Quantum fluctuations during the universe's first fraction of a second created tiny variations in density, some regions slightly denser than average, others slightly less dense. These differences were minuscule, maybe 1 part in 100,000, but gravity amplifies even tiny advantages. Denser regions pulled in more matter, making them denser still. Less dense regions lost matter to their surroundings, becoming emptier. Over hundreds of millions of years, this process snowballed. Small clumps merged into larger clumps, which merged into galaxy clusters, which aligned into filaments. Meanwhile, the underdense regions expanded into voids. The cosmic web is essentially gravity doing its work over cosmic time, turning barely noticeable initial ripples into the grandest architecture in existence. Today, voids occupy roughly 90% of the volume of space. Filaments and clusters make up the remaining 10%, but contain most of the mass. This imbalance defines the universe's character. We live not in a cosmos filled with galaxies, but in a cosmos of emptiness punctuated by occasional concentrations of matter. The KBC void is just one bubble in this foam, but it happens to be our bubble. And that makes all the difference for what we observe and how we interpret the universe. The Milky Way is not at the center of the KBC void, but it's close enough to matter. Measurements place our galaxy somewhere between 200 and 400 million light-years from the void's actual center. That might sound like a huge distance, and it is compared to anything humans experience. But the void extends outward for 1 billion light-years in every direction from its center, making our offset relatively small. We sit well within the underdense region, surrounded by the void's low-density environment in all directions. This position is not random. It has consequences for every observation we make and every conclusion we draw about cosmology. If we were located outside the void entirely, in one of the dense filaments, our measurements of the universe's expansion would look completely different. We would calculate a slower expansion rate, and the Hubble tension would not exist. Our larger cosmic neighborhood adds another layer to this story. The Milky Way belongs to the local group, a collection of about 80 galaxies, including our giant neighbor Andromeda. The local group itself sits within the Laniakea supercluster, a massive structure containing roughly 100,000 galaxies spread across 520 million light-years. Laniakea is enormous by any normal standard, yet even this supercluster resides within the KBC void. Think about that for a moment. A structure containing 100,000 galaxies still counts as part of an underdense region. The void is so vast that it can swallow entire superclusters and still have room to spare. Laniakea forms part of the sparse population of matter scattered through the void, one of the rare concentrations in an otherwise barren expanse. The local group is also influenced by another nearby void called the local void, which is distinct from but connected to the larger KBC void. The local void extends about 200 million light-years and sits adjacent to our position. Our galaxy is rushing away from it at 600,000 miles per hour, pushed by the gravitational pull from denser regions beyond. This motion is separate from the overall cosmic expansion. It's a peculiar velocity, meaning it results from local gravitational effects rather than the stretching of space itself. These peculiar velocities complicate efforts to measure the true expansion rate because they add extra motion on top of the expansion signal. Astronomers must carefully account for these local effects. But inside a supervoid, those effects are amplified and harder to separate cleanly. The void's influence reaches even farther. When scientists measure the motion of galaxies out to distances of 250 million light-years, they find bulk flows that exceed predictions from standard cosmology. Entire regions of space are moving faster than they should be, flowing in coherent patterns driven by the void's gravitational imbalance. The KBC void creates a large-scale velocity field that affects everything within it. Galaxies are not just sitting in an empty region, passively expanding with the universe. They're actively responding to the gravitational landscape, accelerating outward from the underdensity toward denser structures beyond the void's edge. This makes our local patch of the universe more dynamic and unusual than the calm, uniform cosmos that standard models assume. Our position inside the void also affects what we can see. Light from distant galaxies travels through the void on its way to our telescopes. That light experiences less gravitational interaction than light traveling through denser regions. The reduced gravity creates subtle effects on the light's wavelength and energy. Additionally, the void itself influences the distribution of matter we observe. When we look outward from inside the void, we see the shell of denser material surrounding us in all directions. That shell appears as a concentration of galaxy clusters and filaments at a specific distance range. Beyond the shell, the universe returns to more typical density. This creates an observational bias. We're not sampling a random location in the universe. We're sampling from inside one of its most extreme features. Living in the void means living with systematic uncertainty about how typical our measurements really are. Every measurement you've ever heard about the universe's expansion rate might be wrong. Not because scientists made mistakes, but because we're measuring from inside a cosmic hole that distorts the signal. The problem reveals itself when astronomers use different methods to calculate the Hubble constant, the number that tells us how fast space expands. One method looks at the cosmic microwave background, ancient light from when the universe was just 380,000 years old. This light encodes information about the early universe's density and expansion rate. Scientists feed this data into cosmological models and calculate what the expansion rate should be today. The answer comes out to about 67 kilometers per second per megaparsec. That means for every megaparsec of distance, roughly 3.3 million light-year space expands at 67 kilometers per second. The second method looks at nearby objects with known brightness, specifically type Ia supernovae and Cepheid variable stars. These objects serve as cosmic measuring sticks because astronomers understand exactly how bright they should be. By comparing their actual brightness to their apparent brightness as seen from Earth, scientists calculate their distance. Combining distance measurements with redshift measurements gives the expansion rate directly. This local method consistently produces a higher number, about 73 kilometers per second per megaparsec. The difference is 9%. Both measurements are incredibly precise, with very small error margins. Both should give the same answer if cosmology is correct. They don't. This discrepancy is the Hubble tension, and it has reached 5 sigma statistical significance, meaning there's less than a 1 in a million chance it's just random variation. The KBC void explains why these numbers disagree. When we measure the expansion rate using nearby supernovae, we're measuring within the void. The void's low density means less gravity pulling back on the expansion. Matter from the denser regions outside the void gravitationally attracts galaxies within it, adding extra outward velocity. Galaxies appear to recede faster than they would in a typical region. This inflates the local Hubble constant measurement. We're not measuring the universe's true expansion rate. We're measuring the expansion rate plus the void's peculiar velocity field. The effect is large enough to account for most or all of the observed tension. When scientists model how a void of the KBC's size and depth would affect local measurements, they find it could boost the apparent expansion rate by exactly the amount needed to match observations. But here's where it gets uncomfortable. If the void explains our local measurements, then those measurements might be systematically biased by our location. Some scientists resist this conclusion because it violates the cosmological principle, the assumption that Earth does not occupy a special location. The principle states that the universe should look roughly the same from any vantage point once you average over large enough scales. Finding ourselves inside a supervoid that significantly affects our measurements seems to contradict that idea. It suggests we're in an unusual location, which makes physicists uncomfortable. Science has progressively decentered humanity from special cosmic positions. Earth is not the center of the solar system. The solar system is not the center of the galaxy. The galaxy is not the center of anything. And now we're supposed to believe we just happen to live inside one of the largest voids ever observed. The statistical improbability bothers many researchers. Yet the evidence keeps mounting. The void exists. Our measurements are discrepant. The void's effects match the observations. Whether we like the implications or not, the universe might actually be lying to us about its expansion rate. Or more precisely, our location is causing us to misinterpret what we measure. The crisis this creates in cosmology runs deeper than most people realize. Cosmological crisis. The Hubble tension is not just an inconvenient disagreement between two measurements. It represents a fundamental challenge to our understanding of cosmic evolution. Cosmology rests on a framework called lambda cold dark matter, or the standard model of cosmology. This model has been spectacularly successful at explaining observations from multiple sources. It accounts for the cosmic microwave background temperature fluctuations, the abundance of light elements like hydrogen and helium, the formation of galaxies, and the large-scale structure of the universe. For decades, it has been the consensus model because it works so well in so many contexts. But the Hubble tension suggests something is missing or wrong in this framework. When a model's predictions disagree with observations at the 5 sigma level, scientists must take that seriously. The tension matters because the expansion rate determines everything else about cosmic history. If the universe expands faster, it reaches its current size in less time, making the universe younger. Current calculations based on the cosmic microwave background put the universe's age at 13.8 billion years. But if the higher local measurement is correct globally, the universe might be only 12.7 billion years old. That creates immediate problems. We observe stars in globular clusters that appear to be 13 billion years old based on stellar evolution models. These stars would be older than the universe itself, which is impossible. Either our age measurements for stars are wrong, our understanding of stellar physics is wrong, or the higher Hubble constant does not apply to the early universe. None of these options are comfortable. The tension also affects our understanding of dark energy, the mysterious force accelerating cosmic expansion. Dark energy makes up about 68% of the universe's total energy content, according to standard models, but its properties depend sensitively on the expansion rate. If the expansion rate is higher than we thought, dark energy's behavior might be different than current models assume. Some researchers have proposed that dark energy evolves over time, rather than being constant. which would be revolutionary. Others suggest we need to add new physics to the early universe, perhaps an extra burst of accelerated expansion shortly after the Big Bang. Every proposed solution introduces new complications and requires evidence beyond just fixing the Hubble tension. Dozens of alternative explanations have been put forward. Some scientists propose that the measurements themselves contain subtle, systematic errors that have been overlooked. Perhaps dust between galaxies dims supernovae more than accounted for, making them appear farther away and inflating the expansion rate. Or maybe Cepheid variable stars behave differently in different environments, biasing their use as distance indicators. These explanations keep getting tested and ruled out as measurement techniques improve. The measurements are solid. Other researchers suggest modifications to general relativity, Einstein's theory of gravity. Maybe gravity works slightly differently on cosmological scales than we think, which would change predictions for expansion. This route leads into controversial territory, because general relativity has passed every other test thrown at it. The void hypothesis offers a cleaner solution that requires less modification to fundamental physics. It simply states that we're in an unusual location, and our local measurements reflect that, rather than reflecting universal properties. This explanation bothers people philosophically, but requires fewer assumptions than inventing new particles or changing gravity. Recent work has strengthened the void hypothesis by showing it naturally predicts other observations. For example, the outflow velocity from the void should affect not just the expansion rate, but also the motion of galaxy clusters in our vicinity. Measurements of these bulk flows match the void predictions. The hypothesis is making testable predictions that are being confirmed. Nevertheless, debate continues. Not all cosmologists accept the void explanation. Some argue that even a void as large as the KBC cannot produce a big enough effect to fully explain the tension. Others point out that supervoids this large should be rare, and finding ourselves in one just when we develop the precision to measure the Hubble constant seems suspicious. Maybe we're interpreting the data incorrectly somehow. The controversy remains unresolved, which is why the Hubble tension continues to be called a crisis. It's not just a number that's off. It's a signal that our understanding of the cosmos might be incomplete. Understanding how gravity creates this mess requires looking at how forces work in empty space. Gravity inside a void does something counterintuitive. It pushes outward instead of pulling inward. This is not because gravity itself reverses. The force of gravity always attracts mass toward mass. But the geometry matters. Imagine standing in a shallow valley surrounded by mountains. Gravity pulls you toward the mountains, which means pulling you away from the valley center. Inside a cosmic void, galaxies experience the same effect. All the matter lies outside the void in the surrounding filaments and clusters. That exterior matter gravitationally attracts the interior material, pulling galaxies outward from the void center toward the denser regions beyond. The result is an outflow, a systematic pattern of galaxies accelerating away from the underdense region. This outflow is measurable and significant. Astronomers can track galaxy velocities using redshift measurements combined with distance estimates. When they map velocities around known voids, the pattern is clear. Galaxies near void centers are moving faster outward than cosmic expansion alone predicts. The effect is strongest near the void center and weakens toward the edges where matter density increases. For the KBC void specifically, the outflow adds hundreds of kilometers per second to galaxy velocities within the void. Our own galaxy participates in this pattern. The Milky Way is moving at 600,000 miles per hour away from the nearby local void, driven by the gravitational imbalance. This motion combines with other local effects, like the gravitational pull from the Virgo cluster, to create our galaxy's overall peculiar velocity. The outflow has implications for cosmic expansion measurements. When we observe distant galaxies and measure their redshift, we're seeing a combination of two effects: the expansion of space itself and the peculiar motion of galaxies due to gravity. Normally, scientists can separate these components because peculiar velocities average out when you look at large enough volumes. For every galaxy moving toward you due to local gravity, another galaxy is moving away, and the average is 0. But inside a void, the peculiar velocities do not average out. They all point in the same direction outward. This creates a systematic bias that inflates the apparent expansion rate when measured from within the void. The problem compounds at different distance scales. Close to the void center, the outflow is rapid. Farther from the center, but still within the void, the outflow is slower. Beyond the void's edge, the peculiar velocities might even reverse as matter falls back toward the denser filaments. This creates a complicated velocity profile that varies with distance. When astronomers measure the Hubble constant using supernovae at different distances, they're sampling this varying velocity field. If most of their supernovae lie within the void, which they do because we deliberately avoid using extremely distant supernovae due to other complications, the measurement gets boosted by the outflow. The farther out you measure, the less the void affects the result. This predicts that the Hubble constant should appear to decrease with distance, and recent observations confirm exactly that trend. Modeling these effects requires careful calculation. Scientists must estimate the void's size, depth, and density profile, then calculate the gravitational potential it creates. That potential determines how fast material flows outward at each radius. The calculations show that a void roughly 1 billion light-years in radius with a 20% density deficit can easily produce the observed velocity anomalies. The match between predictions and observations is good enough that many researchers find the void explanation compelling. However, the standard cosmological model struggles to explain how such a large void formed in the first place. Computer simulations based on lambda, cold, dark matter rarely produce voids this extreme. When they do, it requires very specific initial conditions that are statistically unlikely. This raises a troubling possibility. Maybe our cosmological model is missing something. If voids larger and deeper than expected keep showing up in observations, perhaps structure formation works differently than standard theory predicts. Some scientists propose modified gravity theories, where gravity is stronger on large scales, which would enhance structure formation and make big voids more common. Others suggest that the universe is simply more inhomogeneous than assumed, which would also make large voids less surprising. Either way, the backwards gravity in voids is telling us something important about cosmic evolution. Our motion through this gravitational landscape is faster than anyone expected. The Milky Way is not sitting still in space. It's plummeting through the cosmos at 600,000 miles per hour, roughly 850 times the speed of sound. This velocity is not from the expansion of space, but from local gravitational effects. Specifically, our galaxy is being pulled away from the local void and toward the denser structures beyond it. The local void is distinct from, but connected to, the larger KBC void, and it exerts a strong influence on our motion. The void itself is not pushing us. Rather, the deficit of matter in the void means there's less gravity pulling us toward it, compared to the gravity pulling us in other directions. The denser regions win the tug of war, accelerating our galaxy away from the underdensity. This speed is difficult to comprehend. 600,000 miles per hour means the Milky Way travels about 167 miles every second. In a single year, our galaxy moves about 5.2 billion miles through space relative to the void. But even at this breakneck pace, the void is so vast that our motion barely makes a dent. It would take hundreds of millions of years to cross from one side of the void to the other, even at this speed. Meanwhile, the void continues expanding due to cosmic expansion and dark energy, growing faster than we can escape it. We're inside the void now, and we will remain inside it for the foreseeable cosmic future. The local sheet adds another component to our motion. The local sheet is a flattened structure of galaxies that includes the Milky Way, Andromeda, and other nearby galaxies. This sheet forms one wall of the local void. The entire sheet is rushing away from the void center at about 260 kilometers per second, which is roughly 580,000 miles per hour. Our galaxy participates in this bulk motion along with its neighbors. The sheet is not static. It's actively being evacuated from the void region, flowing outward like water draining from a depression. This motion has been ongoing for billions of years and will continue for billions more. But there's more to our velocity than just escaping the void. The Milky Way is also falling toward the Virgo cluster, a rich concentration of galaxies about 60 million light-years away. The Virgo cluster contains over 2,000 galaxies and has enough mass to gravitationally attract everything in the surrounding region, including us. This adds another component to our peculiar velocity, roughly 250 kilometers per second directed toward Virgo. Meanwhile, the Milky Way and Andromeda are falling toward each other and will collide in about 4 billion years. That motion adds another 110 kilometers per second. When you combine all these motions escaping the void, falling toward Virgo, heading toward Andromeda, and participating in larger-scale flows, you get our total peculiar velocity of about 627 kilometers per second. That's the velocity astronomers measure when they look at the dipole pattern in the cosmic microwave background temperature. These motions matter because they complicate cosmological measurements. When we observe distant galaxies and measure their redshift, we need to correct for our own motion through space. Otherwise, galaxies in the direction we're moving appear blue-shifted, and galaxies in the opposite direction appear red-shifted, creating a false pattern that mimics cosmic structure. Astronomers have known about these corrections for decades and routinely apply them. But inside a void, the corrections become more complicated because the void itself creates large-scale bulk flows that extend over hundreds of millions of light-years. Disentangling the void effect from the true cosmic expansion requires careful modeling of the local velocity field. Our high speed through space is itself evidence for the void. If we lived in a typical region with average density, our peculiar velocity would be much smaller, maybe 100 or 200 kilometers per second at most. The fact that we're moving so fast indicates strong gravitational gradients in our vicinity, exactly what you would expect from being near a large, underdense region. The velocity is consistent with the void hypothesis and would be difficult to explain without it. This makes our motion a key piece of evidence in the debate over whether the KBC void exists and whether it affects our measurements. The universe may be lying to us about its expansion rate, but it cannot hide the fact that we're racing through it at incredible speed. This motion connects to a deeper principle that the void fundamentally violates. The cosmological principle is one of the foundational assumptions of modern physics, and the KBC void threatens to shatter it. The principle states that the universe is homogeneous and isotropic on sufficiently large scales. Homogeneous means the same everywhere. No location is special or different from any other when you average over large regions. Isotropic means the same in all directions. The universe looks the same no matter which way you look. These assumptions simplify the mathematics of cosmology enormously. They allow scientists to model the entire universe using relatively straightforward equations. Without the cosmological principle, the equations become vastly more complicated, and predictions become much harder to make. The principle has been remarkably successful, accurately describing many observations. But the KBC void represents a major violation of homogeneity. If the void is 2 billion light-years across, with a 20% density deficit, that's a huge inhomogeneity even on cosmic scales. The void is not small compared to the observable universe. It represents a significant fraction of the volume within several billion light-years of Earth. More troubling, we happen to live near the center of this abnormal structure. That seems to contradict the idea that our location is unremarkable. Throughout history, science has progressively removed Earth from any special position. Copernicus showed Earth was not the center of the solar system. Later observations showed the solar system was not the center of the galaxy, and the galaxy was not the center of anything. The cosmological principle is the ultimate expression of this trend. Not only is Earth not at the center, but there is no center because every location is equivalent. The void challenges that worldview. If we live inside an abnormally large, underdense region, our location is unusual by definition. Voids are common in the universe, but most are smaller than the KBC void. Supervoids this large are rare. Finding ourselves in one raises questions about whether the cosmological principle truly holds, or whether it's only approximately true on scales much larger than previously thought. Some scientists calculate that in a universe governed by standard cosmology, a void as large and deep as the KBC void should be exceedingly rare, perhaps a 10 sigma statistical deviation. In a typical random realization of the universe's structure, you might not find one anywhere in the observable cosmos. Yet we're in one. This suggests either we're incredibly lucky or the standard model is wrong about how structure forms. Defenders of the cosmological principle argue that the void does not actually violate the principle, because homogeneity only applies at scales of several hundred megaparsecs or larger. The void is about 600 megaparsecs across, which is right at the edge of where homogeneity is supposed to kick in. Maybe the universe is less smooth at those scales than we assumed. Alternatively, maybe the void is not as extreme as measurements suggest. Different observational techniques give somewhat different density contrasts for the void. If the true deficit is closer to 10 or 15% rather than 20%, the statistical rarity becomes less severe. These counter-arguments preserve the cosmological principle, but require accepting that our measurements are less precise than we thought. Another defense is that we should not be surprised to find ourselves in an unusual location, because observers can only exist in certain types of environments. This is a weak anthropic argument. Perhaps intelligent life requires galaxies to form. And galaxies form preferentially in moderately dense regions, rather than in the densest clusters or the emptiest voids. If most observers live in mildly underdense regions, then finding ourselves in a slight void is not surprising. But this argument only works if the KBC void is not as extreme as it appears. A 20% deficit is more than mild. It pushes the boundary of what the anthropic principle can explain away. The debate over the cosmological principle is not settled. Some researchers believe the void is real and significant, requiring either modifications to cosmology or acceptance that Earth occupies a genuinely unusual position. Others believe the void is an observational artifact, or not as extreme as initially reported. Still others propose that the principle holds on even larger scales, and that the apparent violation is temporary. Future observations should help resolve this. Surveys that map the universe to greater distances and depths will reveal whether large voids are as rare as standard models predict, or whether they're more common than expected. If big voids turn out to be frequent, the cosmological principle survives, but the standard model needs revision. If they're truly rare, we need to explain why we happen to live in one. The origin of these voids reaches back to the universe's first moments. The voids we observe today began as infinitesimal quantum ripples in the first moments after the Big Bang. During a period called inflation, the universe expanded exponentially for a tiny fraction of a second. During this expansion, quantum fluctuations were stretched from subatomic scales to cosmic scales. These fluctuations created slight variations in the density of matter and energy. In some regions, density was a tiny bit higher than average. In others, it was a tiny bit lower. The variations were incredibly small, about 1 part in 100,000, but they were enough to set the stage for everything that followed. After inflation ended, the universe continued expanding, but at a much slower rate. Matter began to clump together under gravity, but the gravitational pulling only amplified the initial density differences. Regions that started slightly denser attracted more matter from their surroundings, making them denser still. This created a positive feedback loop. The denser a region became, the more strongly it pulled matter toward itself. Over millions of years, these overdense regions collapsed into the first stars, then galaxies, then clusters of galaxies. Meanwhile, regions that started slightly less dense lost matter to their denser neighbors. As matter drained away toward the collapsing overdense regions, the underdense regions became even emptier. These underdense regions evolved into voids. The process is called gravitational instability. and it turned barely perceptible initial ripples into the dramatic large-scale structure we observe today. The cosmic microwave background radiation provides a snapshot of these density variations when the universe was only 380,000 years old. At that time, the variations were still tiny, visible only as slight temperature differences of about 100 millionths of a degree. But those temperature differences correspond directly to density differences. Warmer spots had slightly higher density, cooler spots had slightly lower density. Satellites like the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck spacecraft have mapped these temperature variations in exquisite detail across the entire sky. The maps show a modeled pattern of hot and cold spots at various angular scales. This pattern encodes the seeds of structure formation. Scientists can take this pattern and run it forward in computer simulations to predict how structure should look billions of years later. Those simulations reliably produce a cosmic web of filaments, clusters, and voids that closely resembles what we observe. The match between predictions and observations is one of the great successes of modern cosmology. It confirms that our understanding of how gravity shapes structure over cosmic time is largely correct. However, the simulations rarely produce voids as large or as deep as the KBC void. This is where tension arises. The initial quantum fluctuations were random, so every region had some chance of ending up as a void or a filament. But probability distributions matter. Small voids should be common. Medium voids should be less common. Extremely large voids should be very rare. The KBC void appears to fall into the extremely rare category, which raises questions about whether our simulations are missing something. One possibility is that the initial quantum fluctuations were not completely random, but had subtle patterns that enhanced the formation of large voids. This could happen if inflation did not smooth out structure as uniformly as standard models assume. Another possibility is that gravity works slightly differently on large scales than general relativity predicts, which would change how voids form and evolve. A third option is that the universe simply has more variance in structure than cosmologists expected, making large voids less surprising. Each of these explanations requires further evidence. Observations of more distant voids in other parts of the universe would help determine how rare the KBC void truly is. If similar voids turn up frequently, it suggests the standard model underestimates structure variance. If they remain exceedingly rare, it strengthens the case for modified physics or unusual initial conditions. The quantum origin of voids is both elegant and unsettling. It means that the cosmic desert we inhabit traces back to subatomic processes that occurred before atoms even existed. Randomness at the smallest scales propagated upward to create structure at the largest scales. The universe's organization is not designed or predetermined. It's the consequence of random quantum fluctuations amplified by gravity over billions of years. This realization is one of the profound insights of modern cosmology, but it also means that our location within this structure is the result of chance. There's no reason we had to end up in a void rather than in a filament. We're here because the initial conditions in our region happen to be slightly underdense. That accident of quantum chance 14 billion years ago determines what we observe when we look out at the cosmos today. The scale of these empty regions dwarfs human imagination. When you picture the universe, you probably imagine a sky full of stars and galaxies. But the reality is the opposite. The universe is overwhelmingly empty. Voids occupy roughly 90% of the total volume of space. Galaxies and galaxy clusters crowd into the remaining 10%, packed into filaments and walls that surround the voids. This is not just empty space in the sense of vacuum between stars. It's empty in the sense that entire regions, hundreds of millions of light years across, contain almost no galaxies at all. If you could travel through a void, you would fly for tens of millions of years at the speed of light, without encountering a single galaxy. The isolation would be nearly absolute. This distribution creates a lopsided universe. Most of the matter concentrates in a small fraction of the volume. The filaments are crowded with galaxies that interact, merge, and evolve rapidly. Star formation is vigorous. Black holes grow. Galaxies collide and trigger bursts of star creation. Meanwhile, the voids are quiet. A few lonely dwarf galaxies drift through the darkness, separated by vast distances. These void galaxies evolve slowly because they rarely interact with neighbors. They tend to be smaller, fainter, and less evolved than galaxies in dense regions. Star formation is sluggish. Many void galaxies contain large amounts of neutral hydrogen gas that has not yet condensed into stars. They're galactic backwaters, isolated from the busy highways of the cosmic web. The extreme emptiness of voids raises questions about how empty space can really be. Even in voids, dark matter is present. Dark matter makes up about 85% of all matter in the universe, but does not interact with light, making it invisible to telescopes. It's detectable only through its gravitational effect. In voids, dark matter is much less concentrated than in filaments, but it still exists at about 15% of the cosmic average density. That might sound like a lot, but spread over such huge volumes, the amount of dark matter per cubic light-year is incredibly tiny. Additionally, voids contain dark energy, the mysterious component driving cosmic acceleration. Dark energy appears to be uniform throughout space, so voids have just as much dark energy per volume as dense regions. In fact, because dark energy does not clump like matter, it becomes the dominant component in voids where matter is scarce. The interplay between dark matter and dark energy determines void evolution. In the early universe, matter dominated even in underdense regions, and gravity still mattered. As the universe expanded and dark energy became more important, voids began accelerating their expansion. This acceleration makes voids grow faster over time, eating into the surrounding filaments. Eventually, if dark energy continues to dominate, voids will consume more and more of the universe. Filaments will thin out. Galaxy clusters will become isolated islands in an expanding ocean of emptiness. Billions of years in the future, the universe will be even emptier than it is now, with voids occupying an even larger fraction of the total volume. This future evolution is inevitable, given what we understand about dark energy. The universe's destiny is to become increasingly hollow. Understanding the void fraction of the universe is important for interpreting observations. When we measure the average properties of the universe, such as the overall matter density or the expansion rate, we're averaging over both voids and filaments. If we don't account for the fact that most space is void, we might misinterpret what those averages mean. For instance, measurements of the cosmic microwave background give the average matter density of the universe, which is about 30% of the critical density needed to stop cosmic expansion. But that average includes both the dense filaments and the sparse voids. The local density varies dramatically depending on where you are. In a filament, the density might be 3 times the average. In a void, it might be 15% of the average. These variations matter when trying to understand local observations. The 90% void fraction also affects searches for rare phenomena. For example, astronomers searching for distant supernovae or gamma-ray bursts are most likely to find them in the dense filaments where star formation is active. Finding these events in voids is much rarer because voids contain fewer galaxies and less star formation. This creates an observational selection effect. Most of the interesting astronomical events happen in the busy 10% of the universe, not the quiet 90%. We study the universe from within the active regions and mostly ignore the empty ones. But the voids are just as much a part of cosmic reality as the filaments. Understanding them is essential for understanding the universe as a whole. One void stands out as particularly impossible under current physics. The KBC void defies probability in a way that makes cosmologists deeply uncomfortable. Standard cosmology predicts that structures form through gravitational collapse of initial density fluctuations. The larger and deeper a structure, the rarer it should be. Small voids, a few tens of millions of light-years across, are common because they arise from common small fluctuations. Large voids, hundreds of millions of light-years across, are less common because they require larger, rarer fluctuations. The KBC void is 2 billion light-years across and 20% underdense. Computer simulations of structure formation using the lambda cold dark matter model rarely produce anything this extreme. When researchers run thousands of simulated universes and look for voids as large and deep as the KBC void, they find very few matches. The statistical likelihood of such a void existing is extremely low. Some studies have estimated the improbability. One analysis calculated that a void of the KBC's size and depth represents a 10 sigma deviation from the expected density. In statistics, a 5 sigma result means there's less than a 1 in a million chance of it being random. A 10 sigma result is incomprehensibly unlikely. You would need to observe trillions of universe-sized volumes to expect to find even one such void. Yet here we are, living in one. This is not a small statistical anomaly. It's a massive red flag, suggesting something is wrong with either the observations or the model. If the observations are correct, which multiple independent studies suggest they are, then the model must be missing something. One possibility is that the initial density fluctuations after the Big Bang were not as smooth as standard inflation models predict. If inflation produced more power on large scales than expected, large voids would form more easily. This would require modifying our understanding of inflation, which is already a speculative part of cosmology with limited direct evidence. Another possibility is that structure formation proceeded faster or differently than standard models predict. If gravity was effectively stronger in the past, or if dark matter behaves differently than assumed, structure would form more vigorously, creating larger voids and richer clusters. Some researchers propose modified gravity theories, where the strength of gravity varies with scale or environment. These theories can enhance structure formation and make large voids more likely. A third option is that the KBC void is not as extreme as measurements suggest. Perhaps observational biases or systematic errors in galaxy surveys have made the void appear deeper and larger than it really is. Different groups using different data sets have measured the void's properties and found somewhat different results. Some studies find a 20% density deficit. Others find closer to 10 or 15%. If the true deficit is on the lower end, the statistical rarity becomes less severe, though it remains a challenge for standard models. Confirming the void's exact properties requires more data, particularly deeper galaxy surveys that can map the void's extent and density profile with higher precision. Future missions like the Euclid Space Telescope and the Vera Rubin Observatory will provide much better data. The existence of the KBC void has become ammunition in debates about the standard cosmological model. Critics of lambda-cold dark matter point to the void as evidence that the model fails on large scales. They argue that structure formation is not well understood and that the standard model makes incorrect predictions. Defenders of the model counter that rare events sometimes happen and that finding ourselves in a statistical outlier is not impossible, just unlikely. They also note that other aspects of cosmology, such as the cosmic microwave background, match lambda-cold dark matter predictions very well. Abandoning or significantly modifying the model based on one anomalous structure seems premature. Nevertheless, the void cannot be dismissed. It's a real observation that requires explanation. Either we accept that we happen to live in an exceptionally rare location, which violates the spirit of the cosmological principle, or we modify our models to make large voids more common, which requires changing fundamental assumptions about inflation, dark matter, or gravity. Neither option is satisfying. Both represent major shifts in how we think about the universe. The KBC void has become a focal point for cosmological debates, precisely because it sits at the intersection of observation and theory, challenging our most basic assumptions about how the universe works. These vast emptiness regions serve an unexpected scientific purpose. Cosmic voids are the best places in the universe to study dark energy, because voids are the only regions where dark energy dominates completely. In dense areas like galaxy clusters, gravity is strong enough to resist cosmic expansion. Clusters hold themselves together gravitationally despite the universe expanding around them. Even on slightly larger scales and filaments, gravity is still relevant, slowing the expansion of space in those regions. But in voids, where matter is sparse, gravity becomes negligible. With no significant gravitational pull to counteract it, dark energy controls what happens. the voids expand faster than the cosmic average, driven by dark energy's repulsive pressure. This makes voids natural laboratories for measuring dark energy's strength and properties. Dark energy is one of the most mysterious components of the universe. Discovered in 1998 through observations of distant supernovae, dark energy accounts for about 68% of the universe's total energy. It behaves opposite to normal matter and gravity. Where gravity pulls things together, dark energy pushes space apart, accelerating cosmic expansion. The exact nature of dark energy remains unknown. It could be a cosmological constant, an unchanging energy density built into the fabric of space itself, or it could be a dynamic field that varies in strength over time and space. Distinguishing between these possibilities requires precise measurements of how expansion accelerates in different environments and at different times in cosmic history. Voids provide a cleaner signal for these measurements than dense regions. In dense areas, gravity complicates everything. The local gravitational pull from nearby masses affects galaxy motions, making it hard to separate the cosmic expansion from local effects. In voids, those complications are minimal. Galaxies move almost entirely due to cosmic expansion and dark energy. By measuring how fast voids expand compared to predictions, scientists can test whether dark energy behaves as a constant or whether it changes. If dark energy is stronger in voids than elsewhere, or if it was different in the past, that would show up as deviations from expected void expansion rates. Another way voids help is through their shape. Dark energy affects not just how fast the universe expands, but also how it expands in different directions. If dark energy is truly uniform, voids should expand equally in all directions, staying spherical. But if dark energy has variations, or if there are other unknown forces, voids might expand more in some directions than others, becoming elongated or distorted. Observations of void shapes can therefore reveal whether dark energy is uniform or has structure. Current measurements show that most large voids are roughly spherical, which supports the idea that dark energy is uniform. But the measurements are not yet precise enough to rule out small variations. Improved surveys in the coming years will provide much better shape measurements. Studying dark energy through voids is an active area of research. Future surveys will discover and characterize thousands of voids at various distances and sizes. Each void provides an independent measurement of dark energy's effects. Combining many measurements will dramatically improve our understanding. If voids reveal that dark energy is changing or has structure, that would revolutionize cosmology. Even confirming that dark energy is constant and uniform would be important because it would rule out many alternative theories. Either way, voids are proving to be essential tools for probing one of the universe's deepest mysteries. The KBC void, being the largest and closest supervoid, offers the best opportunity for detailed study. Its proximity allows measurements that are impossible for distant voids. The future of voids is one of increasing isolation. Dark energy is accelerating the universe's expansion, and that acceleration has dire implications for the far future. As space expands faster over time, structures that are not gravitationally bound together will drift apart and eventually lose all contact. This process is already happening, but it will intensify over the coming billions and trillions of years. Voids will expand faster than the universe as a whole because they contain less matter to resist the expansion. The filaments surrounding voids will thin out as galaxies within them are stretched farther apart. Eventually, even neighboring superclusters will lose causal contact as space between them expands faster than light can cross. The universe's fate is increasing isolation, with structures becoming islands separated by ever-expanding voids. For galaxies within voids, this isolation will be profound. Currently, galaxies in the KBC void can still see the surrounding filaments and clusters in the distance. Light from those structures reaches us after traveling for billions of years. But as dark energy drives accelerating expansion, light from increasingly distant objects will never reach us. The cosmic horizon, the boundary beyond which light cannot reach us before the universe expands too much, will shrink over time. Objects currently visible will fade from view as their light gets redshifted into invisibility. Galaxies deep within voids will find themselves in increasingly empty skies, with fewer and fewer neighbors visible. The cosmic microwave background radiation will become cooler and dimmer as its photons stretch to longer wavelengths. Eventually, it will become undetectable. This raises a disturbing question for future civilizations. If a civilization arises in a void galaxy billions of years from now, what will they be able to learn about the universe? Their sky will be nearly empty except for their local group of galaxies. The cosmic microwave background will be too faint to detect. There will be no evidence of the Big Bang, no distant galaxies to measure cosmic expansion, no supernovae to trace the acceleration. They will be cosmologically isolated, unable to observe the larger universe because light from beyond their immediate vicinity cannot reach them. Such civilizations might conclude they live in a static island universe, surrounded by empty space, never suspecting the vaster cosmos beyond their horizon. This scenario, sometimes called the dark future, is the inevitable consequence of accelerating expansion. Even within our own void, the long-term future looks lonely. The Milky Way and Andromeda will merge in about 4 billion years, forming a giant elliptical galaxy. This merged galaxy will be the dominant structure in our local group. But the local group itself will become increasingly isolated. Other nearby groups will recede beyond our cosmic horizon within tens of billions of years. The merged galaxy will find itself essentially alone in an expanding void. Star formation will gradually cease as gas is consumed or expelled. The galaxy will fade, containing only old red stars and eventually just white dwarfs, neutron stars, and black holes. The night sky will darken as fewer stars remain active. On even longer timescales, trillions of years into the future, stars will become rare as their fuel is exhausted. Galaxies will consist mainly of dead stellar remnants slowly evaporating into space through gravitational interactions. Black holes will dominate, slowly growing by accreting whatever material remains. Eventually, even black holes will evaporate through Hawking radiation, a quantum process that causes them to lose mass over incomprehensibly long timescales. The final state of the universe will be a diffuse sea of particles and radiation, expanding forever into darkness. Voids will have consumed everything, with the last remnants of structure dissipating into the void's infinite expanse. This bleak future is billions of years away and depends on dark energy continuing to accelerate expansion. If dark energy changes in strength or sign, the future could be different. But current observations suggest dark energy is a cosmological constant, unchanging and unrelenting. If so, the universe's ultimate fate is void domination. The cosmic web we observe today, with its intricate filaments and clusters, is a temporary phase. The true long-term structure of the universe is emptiness, punctuated by isolated islands of matter that grow ever more remote from each other. We live in an unusual time when the universe still has rich structure and when voids are features rather than the dominant reality. Billions of years hence, voids will be everything. One final question remains about our position within this cosmic void. If we live inside a cosmic void, are there other civilizations in the same predicament? This question connects to the broader search for intelligent life in the universe. The distribution of matter affects where life can emerge. Galaxies need sufficient heavy elements to form rocky planets. Those elements are created by stars and scattered through space by supernovae. Too much activity, however, can be dangerous. Violent events like supernovae or gamma-ray bursts could sterilize planets within thousands of light years. Active galactic nuclei in cluster galaxies pump enormous energy into their surroundings, potentially disrupting planet formation. Voids offer a quieter environment where galaxies evolve peacefully. Stars form at a moderate pace. Planets have billions of years to develop life, and cataclysmic interruptions are rare. This might make void galaxies ideal nurseries for complex life. If other civilizations exist in voids, would they develop the same understanding of cosmology that we have? This is a fascinating question. A civilization in a dense cluster would observe rich structure in every direction. Their sky would be crowded with nearby galaxies. They would easily discover cosmic expansion and the Hubble constant because they could observe a large sample of galaxies at various distances. For them, the Big Bang model would be natural and quickly accepted, but a civilization deep inside a void might struggle. With few nearby galaxies to observe, measuring cosmic expansion becomes challenging. The void's effect on local measurements could confuse them, leading to incorrect conclusions about the universe's properties. They might develop alternative models explaining their observations without invoking cosmic expansion or dark energy. This raises the question of whether our own cosmology is affected by our void location in ways we have not yet realized. We think we understand the universe fairly well based on observations from within the KBC void. But what if there are systematic biases we have not accounted for? What if the universe beyond the void looks fundamentally different from what we observe locally? Future observations extending well beyond the void will test this. If distant regions confirm our local conclusions, we can feel confident our understanding is correct. If they reveal systematic differences, we may need to revise our entire cosmological framework. This is the ultimate test of whether void dwellers can accurately understand the cosmos, or whether we are forever limited by our unusual vantage point. We are inside a cosmic hole 2 billion light-years wide. This is not metaphor or speculation. This is observation. The KBC void is real. Its effects are measurable, and its existence challenges fundamental assumptions about cosmology. Whether it explains the Hubble tension, whether it requires modified gravity, whether it makes us unusually positioned in the universe, these questions remain open. But one thing is certain: the universe is far stranger than we imagined, and our place within it is more unusual than we ever suspected. We are cosmic castaways, drifting through a desert of space, measuring a universe that may not be what it seems. Every telescope pointed at the sky, every calculation of cosmic expansion, every conclusion about the universe's fate, all of it might be viewed through the distorted lens of our location. The void surrounds us. It shapes what we see. It determines what we measure. And for billions of years into the future, it will define our cosmic neighborhood as the universe around us becomes increasingly empty, increasingly isolated, increasingly dark. But perhaps that's the most profound lesson the void teaches us. We are not observers standing outside nature, measuring an objective reality. We are participants, embedded in a specific location with specific properties that color everything we perceive. The universe doesn't look the same from everywhere. Our view is local, our measurements are local, our understanding might be local too, and in recognizing that limitation, in accepting that we might be measuring from inside a cosmic hole, we take the first step toward truly understanding our place in the cosmos. The void is not just where we live. It's the lens through which we see everything, and that changes everything.